I will record. And then let's do sharing screen. So we have a little bit of side topics before we start SVM, okay, another learning algorithm, because this also used a lot when you do machine learning, okay? Because so far what we can test if our model is good is to use the accuracy score, but there are another measuring for the performance measuring. It's called the confusion matrix. Okay, confusion matrix. It's also quite useful. Okay, and it will give you, it says, a summary of prediction results. Okay, and this is also for classification. Okay, and it will give you the number of correct and incorrect predictions. Okay, so it's much more detailed. It's not just a percentage score, is it? And here it give us an example regarding two class classification. Okay, so either class 1 or class 2, is it? So what this is the confusion matrix looks like for two class classification. Okay, so you have class 1 and class 2 for the column, and that's for the predicted. And for the row, you have the actual class 1 and the actual class 2, okay? And the cell that's cross between class 1 actual and class 1 predicted, we call it true positive. So over here it says TP, that means true positive. Okay, and then if you take a look by the first row, and the second column, it is, so the class actually should be class 1, but you predict as class 2, is it? So that's why it is false negative, okay? And the same thing for the second row, okay? So here you have class 2 actual, is it? And for class 1, then you predict as class 1, so this is false positive, so false positive. And you also have the class 2 actual and predicted also as class 2, so that's why it's true negative, okay? So this is regarding a detailed description, and it will give you the number, and we will see our examples, okay? So that definition, true positive, false negative, true negative, false negative, okay? And regarding the accuracy, is that the accuracy based on the accuracy is based on true positive and true negative over all of the counts, is it? So that's the accuracy. But like over here said, there are problems if you just use accuracy, okay? Because here says it assumes equal costs for both kinds of errors, okay? So it doesn't always mean 99% always can be excellent. Okay, it doesn't mean that. So it says it can be excellent, it can also be terrible, okay, depending upon the problem, okay? So we need to be careful. So there are a couple of other measures that you can use for the performance, okay? The first is called recall. Recall is what is true positive over true positive plus false negative. Okay, so that's the ratio. It's called recall. Okay, recall. And the high recall then indicate what? This indicates the class is correctly recognized because of small number of false negative. That's easy to understand. Because if this recall is high, then this Fn should be small, etc. So the weight that it takes in this ratio is quite small, is it, for the false negative. That's why it's quite a good measure. And there is another thing called precision. Okay, so precision is what? Precision is true positive, is it, over the sum of the counts of true positive and false positive. okay, false positive. So it says you divide the total number of true positive, etc., and by the total of the true positive and the false positive. So that's for the precision, the ratio, okay. And if this number is high, that tells us what? That tells the example labeled as positive is indeed positive because you have few number of false positive, okay? So this is regarding precision. And here it also give us some scenarios. If you have high recall ratio but low precision ratio, what does that mean? It means most of the positive examples correctly recognized because you have low false negative, but there are also a lot of false positive. Is it so? So you see, you need to be careful. Is it? And the low recall, high precision. What does this tell us? This is says you miss a lot of positive examples. Is it because of the high false negative? Is it? But for those you predict as positive, they are indeed positive. Is it because you have low false positive? Okay, so we can see that's why you cannot just depend on some single measure. That's why we also have the F measure, okay? So over here it says since we have precision and recall, etc., and if we can represent both together, how do we use that? We use this F measure. So F measure, it uses this formula. Okay, so this formula, it means what is a harmonic mean in place of the arithmetic mean, okay, because it punishes extreme values, okay. So it says F measure always near to the smaller of the precision and or like a recall, okay. So this is just another set of performance measure, okay, performance measure in confusion matrix, okay, that's also used quite often with machine learning algorithm, the performance measure. And before we move to the new support vector machine learning algorithm, there are a couple of other things we needed to discuss. The second thing today we will discuss is about regularization. Okay, this is also a huge topic in machine learning. Okay, so it's regularization. So what does that mean? Okay. So we can first take a look. And previously, I don't know if you still remember, we discussed the concept of underfit, is it, and overfit. Yeah, normally underfit is caused by what? Caused by high bias, is it? What means bias? Bias generally means your model, the model you set to train is not a good model, is it? So the erroneous model, is it? Then definitely, is it? Or like fewer features. And of course, fewer features belongs to your model has some big hole, that will cause bias, high bias. So that's called underfit, okay, underfit. So like in this example shown, this is the previous examples regarding the house price prediction. Okay, and initially we use what? We use a linear regression. To predict, is it? So here we have those sample points, and this is that linear regression line, is it? And we can clearly see, is it? This is underfit, is it? The is quite high, is it? So that's regarding underfit. And then about overfit, is it? So for that example, is it, for those sample, you can also use polynomial, is it? Polynomial, is it, for prediction, is it? And it's kind of getting close, is it? So that's one polynomial. And we can also, you can use much more complicated polynomial, is it, to predict, is it, to predict. And then in this case, you can see this model kind of goes through every single sample, is it? But there is a problem, is it? It looks like very good for the training of the training samples, is it? Training sample. But the problem is, suppose this model goes like this, is it? Then once you have some new samples, is it, in those regions, then this will not predict correctly, is it? And so generally speaking, that's called overfitting. This is overfit, is it? Overfit means what? Means fit training data extremely well, is it? Very well, is it? But not good on new sample data, is it? Or new data, is that new data? Is it new testing data or prediction data? So that's why we call it overfit. And generally overfit is caused by high variance, is it? And the variance, variance, generally speaking, it is, so the example, the formula looks like this. So it's a summation of all of your samples, is it? So this is a mean of the sample, is it mean? And you square it, is it? And you divide by the total number of samples, is it? So this is the variance definition. Variance. Generally speaking, what it represents, it represents the spread out, is it, of the data, is it? So if this value is high, so high variance, that means your data spread out a lot, is it? So very spread out, is it? Very spread out. And then you see, you have some samples very spread out, is it, for the training data? And then you just do the high order polynomial, is it? For your model you predict, is it? So it's going to fit very well, is it, with of the training data. But like we just discussed, when you have new data coming in, because maybe in the original, all of the original data, there are a lot of noise. So even though they spread out, but maybe quite a number of them are due to the noise. Okay, then in this case, your focus got shifted to the noise instead of the real data. Is it real data? So that's called overfitting. Okay, overfitting. Okay, then how do we deal with this? Is it, how do we deal with this? So generally speaking, we can use a strategy, we call it, so there are a lot of math background, okay, but I will try to simplify. And this part you already know, is it? That's our goal, to minimize the cost function, is it? So that's for cost function. Okay, and here it shows again for logistic regression, it's similar as what we discussed, is it? So if you add more complicated, is it, polynomial, is it, with that sigmoid, is it, then it can cause overfitting, is it? And how do we generally to address to solve overfitting problem. Is it overfitting one? Maybe the reason it may be caused by too many features. So you consider too many features. Is it because some feature may be just like it serves small turbulence noise? Is it? It's unnecessary. Is it? So one technique is you reduce the number of features. So this just means that it doesn't mean for machine learning the more features the better. Okay, so in overfitting, one strategy to do is to reduce the number of features. Okay, reduce. The second strategy is to do regularization. Okay, regularization. Regularization is to what? Is we keep the features. Okay, keep the features, but we reduce the weight impacts. Okay, reduce the, so because over here theta is our W, is it is the weight. Okay, so you try to reduce the weight impact. And then let's see. And it says works well when you have a lot of features, okay, because each of which will contribute a bit to predicting the model, etc. So that's the regarding the overfitting generally. How do we tackle it? Okay, and here it shows the comparison. This is a simpler polynomial model, is it? And here you have high order polynomial model, is it polynomial? And here is we can do what? Is that suppose we penalize, make it says theta 3 and theta 4 really small, is it? How do we do penalization? You see, you multiply them with some huge number. Is it with a big number? Is it? Then it can, because then it can penalize, because your goal is try to minimize this. Is it? But if you add big number here, is it? So it will shift the focus to this regularization terms. Is it? Instead of the real cost part. Is it real cost part? So that's why we say, okay, this can play some role in the performance, in improving the performance caused by the overfitting. Okay. So regularization, is it? Regularization, and here says if you have two simple hypotheses that can cause the underfitting, is it? But if you have two complicated hypotheses, it can cause overfitting. Okay. So what is regularization? Okay, regularization. Regarding our cost function, it's just you manually add. So you square all of the weights. So this is all of the weights, okay? All weights. And then you square them. And then you let it times some coefficient, is it? And this one, we call it regularization parameter. Okay, lambda, okay. And in sklearn, we will see this basically is 1 over C. Okay, we will see that coefficient a lot. So this can, that parameter C in sklearn, it can do the regularization work. Okay, its purpose is to do regularization. Okay, so now we're getting close to what we need to discuss. But anyway, the general idea that we discussed regarding regularization is just you add this new term. Okay, add this new term to the cost function, because the cost function doesn't supposed to have this term, is it? So you add this term to do to punish, is it? To penalize, is it penalize the weights. Okay, so that's why we call this as the regularization. Okay, then let's see. So, and over here, there is another quite useful tool. It's called learning curve. Okay, learning curve. So learning curve, what is a learning curve? So learning curve is the x-axis. X-axis represent what? Training data size. Okay, so it's increase training samples. Training samples. This is x-axis, and the y-axis is what? Is the error rate. Is the arrow. Okay, arrow. And over here to describe what? So you have the training model. Is it training? And the arrow. Is it the arrow or the arrow? And over here says if the learning algorithm is suffering from high bias, then getting more training data will not help a lot. Okay, so you can see from this diagram that it will not help no matter how much more training samples you add, the error rate is still high. It is not a decrease. Okay, it's not decrease. So this is shows the high variance. High variance means what? Underfit. And generally underfit is caused by what? Is caused by model, not bad model. Is it? Bad model. It may be caused by too few features, etc. Is it? So that's called underfits due to high bias. Okay, so that's underfit. And high variance case is it for the learning curve? Is a learning curve. It says high variance. If the learning algorithm is suffering from higher variance, then getting more training data is likely to help. Is it? We can see. So this is training. Okay, and this curve is for testing, and we call later on we will also learn cross validation. Okay, testing. That and you can see that you can see like this two, the gap getting, so the gap between these two for the arrow is getting smaller. So increase the number of training data is likely to help. Because high variance will cause overfit. Overfit is because of what? Because the sample too spread out. And due to what? Due to sensitive, not to data, sensitive to what? To noise. It's because of the noise. And of course, the more sample data you add, then you may be better to adjust your model, then to get rid of the noise. So it may help. Okay, so here just a learning curve. A lot of time will also help. So here it gives us some summation, okay, regarding the regularization. So getting more training data, it can fix what? High variance, okay. And if you have, here's a try smaller set of feature, can also fix high variance. So this all regarding overfitting. Overfit, so you decrease the feature, decrease the feature. And but for high bias, so underfit, then you can add more feature. So maybe you pick not enough feature, and what? You can also try with polynomial feature, can fix high bias. if you use the linear and it's not good, is it? Then you can try with a polynomial, is it? And then we come to the regularization, the parameter lambda, is it? And lambda, you see, if you increase the lambda, is it? Increase lambda, you can fix what? High variance, is it? Because what? Because that's the extra term, is it? That's the extra term, is it? Because you shift more. So here is the cost function, is a cost function. And if you increase lambda, is it definitely this term will take more role, is it, in your overall cost calculation, is it? So it decrease the role of the weights, is it? So that's why it can fix a high variance. But be careful, okay, later on we will also see our example. It doesn't mean the larger of this lambda, the better, is it? Because you may also have underfit issue, is it? If your model itself is underfit, then you need to what? You need to decrease this lambda, okay? So this is regarding regularization, okay? Also very important concept in machine learning. And then next, let's take a look example, okay? Let's first take a look at this, I think, regarding what we just discussed about regularization. And this example is from chapter 3, okay, that chapter 03. It's still regarding the sklearn one. And it's still regarding the flower, okay, iris, flower. Okay, and in that we have the pedal length and the pedal width. Those are the features, is it? And we do classification here, is it? Classification to classify 3 types of flowers. 3 types of flowers, is it? And here, this part of program, we try to collect weights, parameters, and scores, okay? And we use a loop, okay? With like 10 times of looping, is it? And we are going to use logistic regression, is it? And this logistic regression, this time you see, we also provide this parameter C, is it? What is that C? C is the inverse of that lambda, is it? Lambda is what? Is that regularization parameter. Okay, but be careful over here, we use the inverse of it, is it? So previously we said lambda larger can deal with what? Overfitting problem, is it? Deal overfit, is it? Lambda smaller, it deal with what? Deal underfit. If we don't specify, by default, it is 1, okay? So in sklearn, okay, if you don't specify. So here we try to change, is it? So here is C. C is from -5 to 5, is it? And then what you did is you do 10 to the C, is it? Okay, so that's what you are, so it will, the value should be from 0, 0, 0, 1, is it, to 10⁵, some kind of like this range of value, is it, for our C, is it, for the C. And then we do fit, is it, with our, so be careful also here, is it, this model is already standardized, is it, so it's already scaled. Okay, and scaling data also also plays a very important role, okay, in machine learning. And then with that, you can find of the weights, is that we try to collect of the corresponding weights, okay, weights. And we also collect the parameters, is it? And we also did the prediction, is a prediction. And so that's a general idea about this part. And then let's take a look. So here it shows the diagram, is it? This diagram shows this is that a regularization parameter, is it? And here is the weight coefficient, is it? And regarding either length or weight, is it? You can see the weight change, is it? For the blue one, for the pedal length, the weight with the increasing of the C value, it's increased, is it? But for pedal width, it's decreasing, is it? Okay, and then let's take a further look. And I add more, okay, that's not in the original example. What I add here is I also wanted to know the relationship between C and the accuracy. Is it between accuracy? So I collect all of them, the scores and the C, is it? And here I draw, I get off the value, is it? And from here you can see when C value is really small, the accuracy is not that high, is it? And it looks like it's increasing to certain value, is it? Then it's decrease a little bit, is it? So that's the general relationship, okay? And I also plot the relationship, C and the accuracy, is it? Accuracy. And from here you can see when C is really small, the error rate is very high, is it? That's because what? It's underfit, is it? And then, but from 0.01 to, so here is a 1, is it? Here is a 1, is it? Between this, you can see it grows a lot, the accuracy, is it? Accuracy. And after it reached a certain point, if you keep increase C, it doesn't, it also decrease a little bit, is it? So then it's just like over here it says, after the satisfied accuracy, is it? The regularization strength decreased slightly, is it? But between here, is it? The regularization increased, is it? Yeah, so that's just reflect the relationship, okay? And the next will be, let's take a look the other example. Let's see, is this part? This is, yeah, that's this example. Okay, yeah, that's this example. So we have another concept. Let's share the screen. Okay, there is another concept here. Gradient descent concept we already know, is it? But here is use gradient descent on logistic regression, but with what? Stochastic. Okay, stochastic. And previously what we learned the batch gradient descent. Is it? Batch gradient descent is use what? The weight change depends on, so it's the learning rate. Is it times sigma? Is it I? Is it? And then you have the real Y. Is it? Minus the predicted Y. Is it? And then you times the X. Is it? So over here, this sigma is what? Is regarding all samples. Okay, that's called a batch. Each time, the weight adjustment, is it? It needs all sample data, is it? But just think about in the real world. A lot of time when you do machine, you have millions of data samples. And then each time when you update weight, and it involves a number of iterations also, is it? You will you will perform this gradient descent on all samples. Is it? So that's not going to be very efficient. Okay, sometimes may not be achievable. Is it? So there is a way to get around with it is when we update a weight, we are not going to use all samples. Okay, we use individual one. Okay, so each sample or some mini batch. So anyway, you're not going to use the whole sample space, okay? You use each sample, then to update the weight. Okay, so the weight for each sample you're going to update, also mini batch you're going to update. So this concept, we call it stochastic, okay? And there is another term, sometimes we also call it online learning. Online learning. Okay, that's because it's kind of like streaming is you get one sample, then you're going to update the way you get the next one, you update, is it? So sometimes we call this also online learning. So this concept is called stochastic gradient descent, okay? So that's this concept. And then let's take a look. So in this example, it's just some two exams, then admit student or not, is it? And here is the data. So we have two features and you predict yes or no, is a classification. And you do data standardization. And sklearn support stochastic gradient descent. Okay, stochastic gradient descent classifies it. It's a linear classify. The detailed information you can find the document on the scikit-learn, okay, sklearn library, okay, and linear classification you can use logistic, okay. Tomorrow we will also learn SVM, so you can choose the different solver basically here, and here it lists the different solver, okay. And if you don't specify, by default it use SVM, okay. And here we use stochastic, okay. So it's belong to the linear model, okay. And then you specify here, I want to do logistic regression, okay. I want to use logistic instead of the default SVM, okay. And then you can just fit the training feature value as it, and then we can do predict as it a sample. And here it also shows how do you get a confusion matrix. So at the beginning of the class we discussed, is it to do that you import the matrix, okay, module, and then you just call confusion matrix, then it will give you the confusion matrix, is it? You can also get the accuracy score, okay, nothing new here. You can also get from the matrix, you can also use the classification report. The classification report then will give you precision, recall, F measure also, okay, F measure also, okay. So it will give you a full scale of performance, okay, and you can still get the accuracy score, okay. So over here it's just then we just do the data standardization, is it? So the stochastic, did we already discuss the stochastic? Oh yeah, so over here we already showed how do you use stochastic, okay, gradient descent, okay. And this is just verse. So far what we learned is a batch approach, okay. This is online, the stochastic. And here, the remaining part is just to discuss, okay. You can use first order with quadratic terms. So you use polynomial to, so over here you have example 1, example 2, is it, or not exam 1 and exam 2 is a two feature. And with a linear model, the hypothesis is going to look like this, is it? But here you're going to try also have the square model, is it? So theta 3 x1 2 and theta 4 x2 to the 2, is it? You also, so you make your model more complicated, is it? Adding polynomial term, is it? Then it says, okay, what's your prediction rate? Is it admit or not? Is it? And you can also make it much more complicated. Is it? You can also do cross. Is it? So that's where the theta 0 plus theta 1 x1 theta 2 x2 plus theta 3 x1 square theta 4 x2 square and theta 5 x1 times x2. Okay, so this is a new term, is it? And then you can try to use the stochastic gradient descent or some other model you want to train, is it? And in sklearn, we also have the polynomial feature from the pre-processing. So you can also specify with this. So if you specify with 2, okay, with 2, then the data you will see it where the feature increased from 2 to what? To 6. Okay, to 6. So expand the feature term because what? Because you have the 2 to the square and the cross, is it? So that's why the feature got increased. Okay, so you don't need to write your own polynomial. You can directly call polynomial. Okay, and over here it also shows how do we do regularized logistic regression, is it? This just you adjust the C value, okay, C value. So by default, this first one, C is 1, okay? And then later I change it to 1.5, is it? Then you can see the rate, accuracy rate increased, is it? But it's not always the previous example shows, is it? Sometimes also decrease, is it? And we can also change, you can also manually change the regularization term C, is it? So here it gives 3 different scale of C, is it? And you can see the accuracy rate also increased, is it? So here just shows how do we do the regularization.